Welcome to the Check Socket Digital Design and Fabrication Overview Training. This module is ABC approved for one continuing education credit earned upon successful completion of the quiz at the conclusion of this program. Advances in additive manufacturing, or 3D printing, and materials advances have enabled practices to fabricate check sockets as designed automatically. Comprehensive training, well-defined workflows, and fully integrated standards-based platforms have positioned 3D printing for the O&P mainstream. The business benefits can be profound in terms of reducing fabrication costs while enhancing cash flow and patient experience through quicker delivery of prosthetics. Finally, I want to mention that participants who fill out the evaluation form at the conclusion of this training module will receive unlimited access to Rapid Plaster for a period of 1 month, a $200 value, in appreciation of your feedback. Participants will learn how advances in additive manufacturing and materials are providing an alternative, or in some cases, a complement, to using central fabrication services or traditional in-house fabrication techniques. Participants will also learn through discovery of tools and techniques that can be used to streamline the time between the initial patient consultation and the check socket fitting, even environments with limited technician resources. Oftentimes, this can reduce time frame from days or weeks down to even same day should circumstances dictate. Participants will learn how 3D printing extends CAD/CAM and automation beyond creating a foam carved mold to be used in a traditional fabrication of a check socket to actually creating the actual check socket device to be fitted automatically. We'll also cover digital workflows that enable check socket fabrication without the need to mix, pour, or sand any plaster. What is a digital workflow? Simply stated, a digital workflow is a series of steps that can be performed with hardware and software to accomplish work digitally that would otherwise be performed using plaster with physical tools and techniques. For the purposes of this overview, we can think of the digital workflow as consisting of scan, modify, and print steps. Performing these steps will enable plasterless fabrication of check sockets. When we get to the fit step, the digital and traditional workflows converge. In other words, the tools and techniques used in post-processing of a 3D printed check socket are very similar to those used to prepare a pulled check socket for fitting. This includes how we would remove excess material, grind and polish trim lines, and add a distal attachment. The module is organized by workflow step, starting with the benefits, then an overview, followed by a demonstration using real-world hardware and software employed by clinics today to perform tasks within each step of the workflow. Now let's dive in and cover some of the benefits of the scanning step in the digital workflow. Scanning is quick and easy to perform. Think of going to your primary care physician's office and the natural course of that visit. Each time we go, the information collected includes height and weight at the beginning of that visit. It's easy to collect and documents changes over time and is added to your medical record. Now think about your prosthetic patients. Each time they come in, think of how easy it would be to have a staff member scan their residual limb, then include that scan as part of the patient's electronic medical record. The whole process takes just a minute or two and requires no complex skills or training. If you incorporate scanning patients as part of your practice's standard operating procedures, imagine how easy it would be to document a patient's limb progression over time. Measurements can be taken from the scan whenever needed and can include AP measurements, ML, circumferences at any point in the scan. Comparing scans from different visits makes documenting medical necessity less labor-intensive, more straightforward, and visually obvious when comparing scans side by side or overlaid on top of one another. Shipping plaster models through the mail can add significant delays to your check socket fabrication, is expensive, and can result in lost or damaged models. With scans serving as digital models of the patient's limb at different points in time, there is no need to store, send or receive, and archive plaster models. This can save time while freeing up valuable storage space making your practice more efficient and profitable. Geographically distributed teams are becoming more common, especially while social distancing is a necessity for health reasons. Other scenarios include individual clinics that share patient information within their group. With the internet, it's now possible to share digital models virtually instantly, whether you're in the other room, across the country, or even on the other side of the globe. For example, your practice could easily support scanning a patient at home or in a hospital bed. The completed scan can then be modified from anywhere to design a check socket using computer-aided design or CAD software, then slice to be prepared for printing using CAM or computer-aided manufacturing software. The resulting print-ready Gcode can then be securely shared online for automatic fabrication, either internally or through a central fabrication facility. Now that we've covered the benefits of the scanning step in the digital workflow, let's cover an overview of how it works. In practice today, there are at least 3 different ways to create a digital model of a patient's residual limb. These include casting a patient, scanning the outside of the cast, and then performing a global reduction of the resulting shape to account for the thickness of the cast. This is one of the more popular ways. This allows a clinician with skilled hands to shape the limb with the knowledge of which areas can tolerate support versus which areas will need relief due to sensitivity. Some question why not scan the inside of the cast. The primary reason is that it can be very difficult to capture the inside of the cast, even with tactical scanners, since they perform poorly when trying to capture the distal portion of the cast. Measurement tools and software can be used to verify that the reduction in the resulting positive model is accurate relative to the patient's residual limb. There is also a slight variation of this first technique, which has gained popularity over the last few years, which adds the advantage of casting a weight-bearing shape of the residual limb using such tools as a Symphony Aqua system. Some clinicians report very positive patient outcomes, such as a zero-ply fit as a result. The second way to capture the residual limb is that more experienced scanners will be able to scan the residual limb directly. This requires some practice in scanning technique and is a little more difficult than scanning a plaster model or cast. The trade-off is that the patient's limb will not be shaped by the clinician or through a weight-bearing environment, so those modifications would need to be performed after the digital model is created, namely in the modify step of the workflow, which will be covered next. The third common technique for creating a digital model of the patient's residual limb is to take measurements and then enter those into a software program that can then create an approximation of the residual limb. In practice, this is most applicable to above-knee patients, as these limbs tend to have more fleshy tissue and the socket design is more focused on containment rather than shape conformance. These tools are often referred to as AK by numbers. Now let's cover some scanning considerations to get ready to perform the scanning step of the workflow. First, like any tool in our toolbox, scanners need to be properly calibrated to perform optimally. A properly calibrated scanner will provide accurate digital models consistently. It only takes a few minutes to calibrate your scanner, and your calibration need only be performed once unless there's a problem detected in the scanning results. This will support all apps that use the scanner. We will do a demo of the calibration app for calibrating the structure scanner, the de facto scanner for lower extremity scanning today in O&P. Second, to get a good scan with minimal artifacts or unwanted noise, you'll want to have an environment that is set up for scanning success. This is easy to set up and does not require a lot of space. Optimal scanning environments should be well lit. White light fluorescent lights work well, are inexpensive, and usually exist in an office setting. If not, you might want to consider buying a fixture for this purpose. Scanning environments should be free of clutter, which can create visual distractions, leading the scanner to have tracking issues and pick up unwanted artifacts in your scans that will need to be removed later in the modify step of the workflow. The third consideration when scanning is to focus on matte finishes, as the structure scanner has trouble with scanning shiny surfaces. To achieve a matte finish on a live limb scan, a thin white stocking, knee-high, or talcum powder should be used on the residual limb. These techniques can greatly assist with scanning a live limb. The fourth scanning consideration, which is avoiding movement, also applies to scanning a live limb. The structure scanner tracking relies on objects to be stationary to get a complete, high-quality, accurate scan. Some clinicians use jigs to hold the limb stationary while scanning. We will now do a demo of the calibration app. We'll start by panning slowly across the room so that the calibrator can detect what type of lens. Once it detects that we don't have a wide-angle lens, it'll connect to the calibration server, so network access is required. The bracket for the structure sensor should be flush with the iPad device. Make sure that the camera is not obstructed by the bracket, and then click Start. The app will look for a sunlit area, and if there's not one available, the Enable Indoor Mode button will become available in the lower left corner. Select that to the right. Indoor Mode Acknowledgement, click OK, and then click the Start. Now begin capturing the scene by moving around and pausing as you go, paying attention to the scene complexity meter in the upper right-hand corner. Once a sufficiently complex scene has been found, it'll begin calibration process. We now see that there's a light green, which represents the color depth. And what we're trying to do is drag the light green area over the object in the application. So in the chair, we see the edges of the chair in the light green, and we're using our fingers to drag the shaded area over the image. Same with the plant. So we're going to take a variety of shapes while we're calibrating using the advanced mode. Piece of furniture has nice edges. You can see the separation of the shading versus the image, so we're going to overlay those. And then last, we'll finish with a positive model that we're going to use for the scanning. And once the color depth has been aligned perfectly over the positive model, we're going to go ahead and click the Save Calibration, and that calibration will then be uploaded to the structure sensor, and we're now ready to scan. Now that we've calibrated our structure sensor, we're ready to scan our positive model. We'll start by hitting the scan button and then pinching gestures to put the bounding box to include the entire positive model. Then we'll begin by scanning roughly 40 centimeters away from the positive model, walking all 360 degrees around the positive model. And as we walk around, we'll see that the model begins to fill in as data is captured. This is what we call keyframe data. We follow the on-screen instructions and pause as necessary. Once the scan is done, we click the Done button, and that will then allow us to preview our scan, looking primarily for any holes or gaps that might have been missed when we scanned. It's very easy to go back and rescan as needed. We want to make sure we capture a full scan. Once we have, we'll go ahead and email that to raw scans and make it available for the modify step coming up next. Now that we've covered the scan step of the digital workflow, let's move on to the modify step. In this step, we bring the world of plaster into the digital age. Here are a few benefits from modifying digital models using CAD, which stands for Computer Aided Design Software. One of the benefits includes the ability to perform a global scale modification to accommodate limb volume changes due to increase or decrease in limb volume. This makes it easy to accommodate volume changes when the shape of the limb remains constant, something that's very difficult to do in plaster. Another benefit is the rapid integration of brims and distal attachments by using templates that can be pulled in, positioned, merged, and blended with the digital model in the modify phase of the digital workflow. These can greatly accelerate the check socket design process. The history feature of CAD programs allows a user to undo or redo an operation or series of operations performed on the digital model during the modify step. Remove too much material? No problem. If this happens, the user can just click the undo option. Anyone who's old enough to remember typewriters without whiteout tape will appreciate the analogy to word processors and their ability to undo typos with the click of a mouse. Word processors were definitely a typewriter killer. Another benefit is that digital modifications can be performed on a computer anytime from anywhere there's an internet connection. No need to pour, mix, or wait for plaster to dry. The implications of this benefit are profound and appropriate for today's socially distanced work environments. Another benefit is that we can use an electronic preview function to check a check socket before it's fabricated. So we can preview the check socket, spin it around, look inside it, and look for anything that might look like structural issues that could impede the ability to do a static and a dynamic test with the patient. Now we will cover an overview of the modify step and the tasks required to complete. The first task is to remove any artifacts that are picked up in your scan. The cleaner the scanning environment, the less artifacts that will have to be removed in this step. The second task is to orient the model. This is necessary for the camera feature to work correctly so that you can quick switch your view from anterior to posterior, medial to lateral, and from distal to proximal. In addition, the measurement tools, including the height, circumference, AP, and ML tools, rely on the model to be properly oriented relative to the print bed. This would include the anterior portion of the model facing the user, with the distal portion of the model closest to the print bed as represented by the gray line on the screen. When scanning the outside of a cast, users will want to perform a reduction, which is a scale global reduction, to account for the thickness of the cast. While building confidence in the digital workflow and the reduction percentages, it's especially important to validate measurements to patient limb to ensure accuracy. Once the scale and measurements are confirmed, clinical modifications on the positive model can then be performed. These include any modifications that you would do in plaster. After completing the clinical modifications, users can add a brim using the tools available to align, merge, then blend the brim for a smooth transition to the rest of the model. This can greatly accelerate device design. The same applies to distal attachments, where users can add, align, merge, then blend distal attachments also for a smooth transition to the rest of the model. The final step is the CAM step, or computer-aided manufacturing, sometimes referred to as slicing, where the user selects the material and the kind of device they want to print. For our example, PCTG puck lock with 2.5 millimeter thickness. This translates the solid shape, which is an STL file, to a sliced printer-ready Gcode file. We'll begin our demo of Rapid Plaster by going into the raw scans folder and opening the scan that we just took. And we'll notice that the scan, even though the scan looks solid, it includes the tabletop. So what we want to do first thing is to remove that artifact, as I'll refer to it. And we're going to use the plane cut tool to be able to remove that artifact. So the plane cut tool cuts within a plane that's parallel to the print bed, so we're using the gray line just below the positive model as a guide. We've cut off the tabletop, and now we're going to use the move tool to position the positive model such that it is in proper orientation for us to use different tools like the measurement tool and the camera tool. So we're going to have the proximal end down towards the gray line, which represents the print bed, and then we're going to have the anterior facing us, and then we will try to align that on the center of the print bed. So we'll look at it from a topical view to be able to see whether or not the orientation is proper. Once we have the proper orientation, we'll hit the reset view, which will always put the view in the same location. But again, what we want to do is make sure that the positive model is centered on the print bed, visually at least. No need to count individual squares. And then once it's centered on the print bed, what we're going to do next is we're going to verify the measurements. So it's always a good idea when we've done a scan to verify the measurements, and we're going to use a circumference tool. It gives us 2.5 centimeter intervals in between the circumferences, which can be moved by moving the cursor up and down the model. We'll also look at an AP measurement, which can be measured by moving the cursor up and down the model, and measures an AP line through the positive model. And then the ML measurement tool works much like the AP measurement tool, except in an ML orientation. It allows you to take ML measurements up and down the model by moving the cursor vertically up and down. You can also use the point-to-point measurement tool, which is handy. So from one point to another arbitrary point, and then once we've selected the arbitrary points, the distance will be shown in the upper right-hand corner. There are height tool measurements that are valuable, and we'll use the height tool later on when we add a distal attachment in a creative way. So now that we've got our model oriented, we've demonstrated that our measurements are correct, what we want to do now is some minor clinical measurements, minor clinical modifications. So we're going to select the carve build tool, and we're going to select the carve option, and then we're going to do a little carve out around the patella tendon. And this is a common modification. It's similar to how you would do it in plaster, except in this case we're using a digital model, and then we're going to smooth that so it's a nice smooth transition, not a sharp cut. The next thing we'll do is we'll spin the model 180 degrees, and we're going to take some material off the posterior portion of this model where the patient is more likely to tolerate support based on the anatomy and the fleshy tissue that would be anticipated in that region. We'll just take off a small amount of material with a few strokes, and then we'll use a smooth tool to blend that in, just so that there's no high or low points, that it's a nice smooth transition. And we'll keep smoothing that off, and we'll smooth other parts of the model just to clean things up a bit. Again, all in the objective of a nice clean fit. The next thing we're going to do is we're going to add a posterior shelf, and this is a fairly common thing to do. So we have a BK patient, left BK, and we're going to select posterior brim 1. First thing we're going to notice is that it's a separate selectable object, so we're going to use the move tool associated with our shelf and spin that 180 degrees in attempts to get that in proper position and alignment relative to our model. We will look at the model from multiple orientations. This is where the camera tool and the alignment that we set up initially is so important. Looking at it from the top, we will then reselect the shelf and rotate it slightly so that we can get that so it's perpendicular to the very posterior part of the positive model. And we can use the printer bed grid as a guide for that. Very helpful tool. And then we'll slide it into position. We will look at it from both medial lateral positions, ensure that the shelf is low enough relative to the MBT, and we can see the shelf through the model. You'll see the outline of the shelf as I move the model back and forth, and get that in position to be able to merge it. So we've gone ahead and merged that shelf, and we'll remesh it so that we can align the shelf resolution with the resolution of the positive model. It also makes it easier to blend. We're going to use the flatten tool, and then we will select the fill low option, and then just run our finger down that line a few times if we're on a touch screen. And then we'll remesh that, make it easier to smooth. And then we'll spin it 180 degrees, and we're going to do the same thing on the other side, except this time we're going to be able to do it in just a couple of strokes. And we've blended the shelf in. But at this point, we want to cut the angle down, because right now it's about a 90-degree flare, which is more than the patient needs and also very difficult to 3D print without supports. So we're going to use the build tool. We'll adjust the brush size and the intensity so that we can add a little bit of fill here with just a few strokes. So we're going to run our finger around that twice. We're putting a little bit of plaster in there, virtual plaster, and then we're going to blend that in with the smooth tool. So just a few strokes, we've been able to cut that angle from 90 degrees down to about 45. Be a much cleaner flare. Now, at this point, we still have a piece of the shelf that protrudes past the top of the positive model. So we're going to go ahead and use the plane cut tool to plane cut the protrusion. And now we should have a nice level top to the positive model. The shelf will not protrude past it, but we flush with it. And at this point, we should be in good shape to add our distal attachment. So we're going to add a puck lock here. And this would be used for a bulldog puck lock, for instance. You'll see there's a line on the puck lock dummy that we just brought in. That's where the puck will be. So we don't want the distal portion of our positive model to go below that line. It's a guideline. Otherwise, the patient would be running into the puck and be very uncomfortable. So we're going to now use the measurement tool once again, but in this case, we're going to use it as an alignment tool to be able to see center of model relative to center of the distal attachment that we're adding. And so we'll make a series of adjustments here, all in attempts to approximate a bench alignment for our check socket, so that when we do our static and then dynamic fitting with the check socket, that it'll be best positioned to provide a positive outcome for the patient. So again, we're going to use the height tool. You can see that it's still a little bit off center, so continue to make a few adjustments here to the alignment. We see from the posterior that maybe rotated a little bit to get a better alignment. And then we'll use the measurement tool once again. We'll drop that virtual laser or plumb right down through the model, through the distal attachment, a few more adjustments perhaps. And as we adjust that, we'll move the puck over a little bit on the distal attachment, and then we'll do another check with the measurement tool and see if we're getting close here. And having a proper alignment, as you know, is super important. So being more judicious at this point in the process pays big dividends later on. So I'm going to do hopefully one last movement here. We'll do one last measurement, hopefully. And if things look like they're centered and they're on point, then we're going to check our distal and go ahead and merge that right into the positive model. So now those are one object. And what we want to do now is, as a last step before we prepare this for printing, we're just going to smooth that transition point a bit. So we're going to go ahead and remesh that, have the resolution aligned with the positive model, and then we're going to run the smooth tool over it just a few times, just a few strokes. Just had a nice smooth finish, so when we print it, it has a nice smooth transition point there. And at this point, we've done everything on our positive model. We're now ready to do what's called slicing. This is where we transition to the CAD portion of the program. The CAD portion simply means we are going to slice, as it's sometimes referred to in 3D printing. We're going to slice this shape file into a 3D printable file with selected 2.5 millimeter thickness, and then I'm going to name the file PID-123, L for left, BK for BK, and then PL for puck lock. So I provided a meaningful name, so as I'm printing these files, I'll have an idea on what patient the file is for and also what kind of device I'm printing. And so right now, the shapefile is being converted into a Gcode, which is a printable file. And before we print that Gcode, we're going to preview it to make sure that there's no nuances that could somehow affect the automatic fabrication of this check socket. So we're looking for any gaps in the lines and the layers, and you'd see a space, a vertical space that would run vertical to the print bed. Typically, like it would look like there was a layer or two missed. Generally, those kinds of issues are caused by overhangs. So if you have a posterior shelf that's more than 60 degrees and you don't have supports, for instance, that could cause a problem. But everything looks good here. So now we're going to go look to the right and note some key information. How much filament, so we have enough loaded.
how long is it going to take so we can schedule our prints appropriately, and then how big of a print is it. Once we've done that, we're ready to download our Gcode and just a few steps away from beginning our automatic fabrication.
Now we're going to move on to the print step in the workflow and talk about some of the benefits. The first benefit in the print step is the ability to produce devices with walls of uniform thickness. Device wall thickness can be varied through the CAM, or computer-aided manufacturing component. This is referred to as slicing in 3D printing. All of this is done programmatically so that the same settings produce quality results every time. Perhaps the single biggest benefit of digital fabrication is automation. Devices are 3D printed, and like carvers, can do most of their work unattended without the need for human intervention. Since labor is the largest cost element in check socket fabrication, automatic device fabrication is the biggest benefit. CAM automation leads to scalable, predictable, repeatable results. Through 3D printing, a single technician can simultaneously fabricate many devices at once. This is rapidly becoming the new normal in O&P. In addition to business benefits, there are environmental workplace benefits. Fabrication through 3D printing requires less power, produces less heat, consumes less materials, and makes less noise than traditional fabrication workshops. Fabrication footprints can be reduced from an entire workshop room or rooms to less than the space required for a refrigerator. With sufficient build volume, a characteristic of 3D printers, devices for most above-knee and below-knee patients can be automatically fabricated. Now let's review the print check socket step overview. Prior to printing a device, it's necessary to prepare the print bed. This ensures that the device to be printed will adhere to the print bed and be able to be easily removed once the print completes. This step is more typically a verification step, as the same bed preparation will support many prints. The file created by the CAM will include instructions for the printer to heat the print bed to proper temperature to ensure check socket print quality. Next, we will want to make sure that we have sufficient filament to complete the check socket print as designed. You may recall during the demo of the modify step, during the print preview task, one of the key pieces of information that we noted was the estimated filament usage, and it was for this reason. Typical filament spools are 2.5 kilograms, conservatively averaging 5 devices per spool. Advanced printer features include pause, resume features in case filament runs out and needs to be reloaded during the printing of the device. Calibration of the print bed is much like the calibration of the scanner in the scan step, in that this calibration is generally performed once and need not be reperformed unless or until a printing problem is encountered. If the print nozzle is too close to the print bed at the start of the print, no filament can be extruded. If the nozzle is too far away from the print bed at the beginning of the print, adhesion of the printed device to the print bed will suffer. Bed leveling is also very important. Like calibration, bed leveling is generally performed once and need not be reperformed unless or until a printing problem is encountered. Advanced printer features include programmatic bed calibration and automatic bed level, and these are enabled by a probe and a programmatic bed compensation program run by the controller. Once the CAM-generated printer file, also known as a Gcode, is submitted to the printer, it is recommended that users monitor the print for the first few minutes while initial layers of the printer are being extruded onto the printer bed. This is to ensure proper initial layer adhesion and quality. After that, programmatic automation will take care of the rest of the print. This is what makes 3D printing so scalable. Once the print is complete, the check socket can then be safely removed from the print bed and be prepared for patient fitting, much the same way a traditionally pulled check socket would be.
Now use the web interface to connect to our printer wirelessly, and we will go ahead and upload and start the Gcode that we created in the modify step. and we'll see the upload progress in the dialog box as a file is uploaded from our laptop to the Emergence Pro printer. Once the file has been uploaded, we'll get a confirmation that the G-code has been uploaded, and the print will soon begin on our Emergence Pro printer. Once the print file has been submitted and accepted by the printer will warm up both the extruder as well as the print bed to the desired temperature in the G-code. Then the printer will begin its homing sequence, which will go to the back edge of the printer. It will home the X and Y axes, and then lower the print bed until it hits the probe coming back up and calibrate the print bed on the Z-axis home. Once all of the axis has been homed, the next thing that the printer will do is perform a 24-point bed probe to ensure that it can auto-compensate any bed level issues that it may encounter. This will ensure that you have a high-quality print while compensating for any differences in bed height according to the heat map that is generated as a result of the 24-point bed probe. This is what's known as auto-leveling. After completing the 24-point probe, the printer will bring the extruder to the front of the print bed and prime the extruder by extruding a small amount of material before beginning the first layer of the print. From a fabrication standpoint, most of the print is automated, but it is important to monitor the first few layers of the print to ensure that the extruder is extruding material properly and that a good first layer of adhesion is applied. After getting a first good layer or two, the printer can largely fabricate the device unattended. This is what makes additive manufacturing so scalable, in that one technician can manage many 3D printers printing check sockets simultaneously. This allows the process to be very scalable while not requiring additional incremental labor to produce many more devices.
The last step in the workflow is the Fitstep. The Fitstep is where the digital workflow transitions back to a traditional fabrication workflow. Once the printed check socket is removed from the printer bed, the trim lines can be ground and polished using the same tools and techniques used for pull check sockets. After the trim lines are finished, attach hardware distally. For patient safety, it is recommended that clinicians fiberglass reinforce the transition point between the distal attachment and the socket contact point with the residual limb. Once the check socket has been sufficiently reinforced as judged by the clinician, it's now ready for what many refer to as a static and then a dynamic test. A static test would be standing and putting weight on the socket, and a dynamic test would be walking in parallel bars with the socket on. This will help ensure that the fit under load is comfortable and that the alignment will support a proper gait. Adjustments, if any, can be made using a heat gun or torch, much like how adjustments are made on a traditionally fabricated pulled check socket. Thanks for your time and attention. We hope that you found the check socket, digital design, and fabrication overview training module both interesting and relevant to your practice. To receive ABC credit, please go to the first web address listed on this slide and complete the 10-question quiz. 8 out of 10 correct answers are required to receive your ABC credit. We also value your feedback, so as a bonus, in exchange for filling out our training evaluation form, you'll receive a 1-month full access pass to Rapid Plaster, our CAD/CAM software, a $200 value. Feedback can be submitted at the second web address listed on this slide. If you have any questions while you're completing the quiz, or you'd like to learn more about digitally designing and automatically fabricating check sockets, contact us by phone at 518-371-2684 or email us anytime at info@pva.net.